Hello everyone. Today we're going to be talking about the C++ build process, which is just a super foundational topic, super fundamental topic to understand if you actually want to know what goes on between your source code looking like C++ code and actually running on your machine. So that's what we'll be talking about today. The contents for today, it's broken up into three sections, as the build process is. Build process is split up into three sections. There's the preprocessor, there's the compiler, and the linker. And the output of each section serves as the input into the next section. Each stage transforms the code in some distinct way, producing intermediate outputs. And today we're going to be looking at how we can examine the outputs between each section and gain some insight into how our code is actually working. All right, so let's get into it. We'll start off with the preprocessor. This is the first stage of the build process. The preprocessor's job is basically to edit the source code text file, because your source code really is just like a glorified text file. So the preprocessor edits that text file according to a set of preprocessor directives. Preprocessor directives begin with this pound symbol. It's actually called an octothorpe, by the way. It begins with a pound symbol, and they're processed line by line before compilation begins. All right, so we'll go through some of these most important preprocessor directives, starting off with the text replacement directive family. There's the pound define directive, which is used to define macros. A macro is like a symbol that the preprocessor replaces with some value or some expression or some code snippet. And pound define just instructs the preprocessor to replace every occurrence of a defined symbol with its corresponding replacement string. So this, for example here, would allow me to define preprocessor constants like such. If I say pound define pi is 3.14, and then what the preprocessor will do is it will search through my entire file here, find all of the symbols that look like pi, and replace them in text with 3.14. So that means if I go ahead and run this, we'll get the expected output printing to the console. People call these preprocessor constants, but I kind of don't like that term, because I can just do this, like pi 4, and this will, I think it'll produce a warning, but it'll run. So this doesn't like produce any errors in C++. Hence, I don't really like to call them preprocessor constants, because in what sense are they constant if you can just redefine them instantly? But I digress. Anyways, so that's pound define for defining macros. It's important to remember, and I'm going to say this over and over again, that the preprocessor does not understand C++ semantics, and it just performs text substitution. This lack of sort of type checking or validation, it can lead to unexpected behavior if you're not using macros carefully. All right, so pound define can also be used to define macros without a replacement string. And in this case, the macro is simply like a placeholder for some symbol. It's like we're not replacing debug with anything necessarily. We're just saying to the preprocessor, this macro exists. And this is mostly used for like conditional compilation purposes to enable or disable compilation of certain parts of the code. We'll see more about that in a few sections. The pound define directive, it can also be used to create function-like macros that can accept arguments. For example, here I've defined a function-like macro called square, which takes in an argument x and just replaces it with x times x, as you would if you're squaring a number. So if we call square with 5, then it's going to replace it with 5 times 5, which will of course print out 25. However, it's really worth noting here that the potential for unexpected behavior increases significantly with function-like macros. And this is because the preprocessor, once again, simply performs text substitution. So I'm going to show you an example of this. We will look into square.cpp, where here I've defined the square macro again, but now I'm calling it with 3 plus 3. And so, okay, you might expect, take a moment, pause the video perhaps, see if you can guess what this will print out. And you might expect it to print out 36, because that's what 6 times 6 is. But if we run it, it won't give us 36, it'll give us 15. And so, okay, that's confusing. But if you actually go ahead and just manually expand the macro, then you can see exactly what's going on. It just expands it into 3 plus 3 times 3 plus 3. And now the problem is that the compiler completely, or rather the preprocessor completely disregards our intended order of operations. So it made it into this expression, which of course does evaluate to 15, and it does everything as expected. It's just that it's not exactly what we expected as the programmer. So, okay, for this specific type of error, there's a pretty easy way around it. We could simply wrap everything with parentheses. And that's what I did here in square2.cpp. I wrapped the definition of x within the macro in parentheses. So now, of course, if I come down and I say standard cout square of 3 plus 3, then we're going to get the expected output on this line, right? So it'll be 36 here. So that makes sense because we've used parentheses here, but it's still prone to unexpected behavior with this other example I have, where I define an integer I to be 5, and then we just print out the square of the incremented version of I. And once again, you might expect this to simply increment I to 6 and square it and give us 36. But actually, I think we're going to get 42 here. Yes, we get 42, and the compiler is actually nice enough to give us a warning that there are multiple modifications to I going on, which gives us a hint as to how the preprocessor handled this. If we manually expand it again, then what we get is plus plus I times plus plus I. And now you can see the problem is that there are 2 modifications to I going on, which leads us to multiplying 6 times 7, giving us 42, not exactly what you'd expect. And at the end of all this, I will actually be 7, even though it looks like we only incremented it once. Okay, so that's that. The function-like macros defined with the preprocessor are very prone to unexpected behavior, as we just saw. And unfortunately, there's no way to combat this second type of problem that I showed, or many other types of problems with more complicated function-like macros. So for this reason, I highly recommend that you basically leave work up to the compiler whenever possible. And I have this rule of thumb here: the compiler is smart and the preprocessor is stupid. The compiler can and will try to optimize your code. It will catch potential bugs. It'll give you nice, helpful warnings and errors. But the preprocessor will gladly destroy your entire code base and hide it from you. So that's kind of my take on that. The choice between a function-like macro, if you're given the choice between a function-like macro and a proper C++ function, you should almost always prefer the function, especially with modern C++ features such as lambda and compile time expressions. Okay, right, so now that we have condemned preprocessor macros, especially the function-like macros, why don't we talk about how we can rid them from our code base entirely? The undef directive can be used to undefine a previously defined macro. Pretty simple. If we pound define pi, then we can use pi, but if we undef pi and try to use it again, it's going to produce an error that pi is an undefined symbol. So that's quite simple. And the reason you would want to do this, of course, is that you just want to prevent naming conflicts. By undeffing macros that are no longer needed, you don't run the risk of having accidental naming conflicts or redefinitions. We'll move on to our next sort of family of preprocessor directives, which are the include directives. The include directive is used to include the contents of another file in the current file. You can think of it as like copying and pasting the contents of some other file in place where we include it. There are 2 variations of pound include. There's the angle brackets include and the double quotes include. The difference between them lies in where the preprocessor will search for the given file. With the angle brackets include, the preprocessor is going to search something called the include path, which is like a special directory or a list of directories on your machine that contains various standard libraries and headers. With double quotes, it's actually going to search the current directory first, and if it doesn't find the file there, then it will search the include path. So if you think about it, you could use the double quotes for every single include, but that's not really best practice. I think best practice would be to use angle brackets for standard library headers like IOStream, and then use the double quotes for basically everything else, your local files or project-specific files. The pound include directive essentially just copies and pastes the contents of the included file in place, and I'm going to say that again and again. It's really quite simple. If we have these two these two files here, main.cpp and x.cpp, where main.cpp includes x.cpp, this is functionally the same as this main.cpp, where we just put x.cpp's contents right in place, right? So those are functionally the same thing. And to further demonstrate the sort of super literal nature of the pound include, the dumb literal nature of pound include, I rewrote hello world in a truly terrible manner. So we have this hello world program which includes IOStream, and then there's 5 more include statements down here. Why don't we just take a look at what each one of them is. First, it's int.cpp, which just has the word int, and then we'll look into the main function.cpp, which just has main, and then we'll look into openbrace.cpp, which just has an open brace. And maybe you can see what's going on here is that we're constructing the hello world program basically line by line or piece by piece. And so, of course, when we go ahead and run this within hello world.cpp, it's just going to make hello world because the include directive just takes contents and pastes them in place. That's it. That's like all it does. It's solved. So, of course, this file will turn out to look something like this, which, somewhat resembles a normal-looking hello world program. It should go without saying, though, that this is not how you should write your programs. Typically, you shouldn't put every single symbol into a different file and then just include them all in one place. So a proper approach to modular file structure is what we're going to discuss now with header files. Header files are commonly used in C++ projects to organize code, especially in larger projects. Their primary role is to do what's called declaring an interface to a module or a library, which allows you to separate the declaration from the definition, or separate the implementation from the interface, you could say. But while this is sort of their primary role, as with most things in C++, there's no strict rules about what you can or should put into a header file. It's mostly up to your project conventions or whatnot. Here's an example of a simple header file called mylib.h, where we just declare a function called greet. Now, the definition of greet would typically go into the corresponding source file, like mylib.cpp, where we just define the greet function. And notice that we #include mylib.h so that we inherit the same declaration up here. All right, so that's header files. They don't actually require too deep an explanation, I think. A lot of people are confused by them, but I think that if you properly understand the build process, then you'll just be able to reason through exactly what goes on with your header files. So they don't require too big an explanation. They're really just text files, again, where we #include them, and the places where we #include them, you just have to reason through what's actually being included. Once again, the reason for header files is just so that we can separate our declarations from definitions, which helps to improve the code's readability and modularity. We will carry on now to conditional compilation. Conditional compilation, it's where the preprocessor basically decides if a piece of code is going to be included or excluded in the final executable. It does this through a set of directives, like #if is one of them. It evaluates some condition and includes the subsequent block only if that condition is true. So let's say we #define debug to be 1, and then we say if debug, include this block. And then there's the endif directive to terminate a conditional block. It's worth noting that the condition variables, like here, debug, they have to themselves be preprocessor macros, right? We can't just have a normal variable go there because the entire preprocessing stage happens before the compiler ever recognizes that a variable exists. Right, so these have to be preprocessor macros themselves. You can also use the #else and #elseif directives to create sort of preprocessor branching logic within your directives here. So this is pretty simple. We just say define control to be 2. You could say if control is 1, elseif, else, endif, and you can just use these sorts of structures to decide which code to actually include in your executable file. Next, there's the ifdef and ifndef directives, and they give you control by allowing you to include a block if a macro is defined with ifdef or not defined with ifndef, if not def. For example, we have a macro called debug, and we just say if debug is defined, then we'll include this block. A very common use case for a conditional compilation is something called an include guard. You'll see these a lot, especially within header files. An include guard, it prevents the same file from being included multiple times within a translation unit. If you don't know what a translation unit is, then just hold on for 2 minutes. We're going to talk about them in the next section. But for now, just know that if a header file was included multiple times, it could cause redefinition errors and other compilation errors. An example include guard for mylib.h might look something like this, where we just have this symbol here, mylib.h included, and we say, if that symbol is not defined, then define it. And then we put all of our file contents here within this whole structure. So the end if goes at the very end. So it's all within the conditional compilation block. And what this will do is the first time mylib.h is included, the preprocessor is going to define this macro. It's going to reach this line 2 and define this macro. And then if we include the file again, then basically the entire file's contents will be blocked out by the conditional compilation because now this macro is defined. So it's not going to include the file again, thus avoiding redefinition errors. So you'll see these this sort of structure a lot, especially in header files. That's what it's doing. It's an include guard. We'll move on now to translation units. Translation unit is like a term that's thrown around a lot in the C and C++ world, but I think some of the people that use the term, I don't know if they could define it properly. It's a sort of a hard term to define properly, I guess. But how I'm defining it is just the output of the preprocessing stage is a translation unit. It's like the preprocessed result of a single source file with all of the directives expanded. And all of the directives expanded means that a translation unit includes any like header files or other source files that have been used via the #include directive, as well as any header files that those files might have included, right? So if you have, like, you include one file that includes another file that includes another file, all of those files are going to be present within the translation unit. And as a result, because we're only dealing with preprocessed directives, the output, the translation unit, is still valid C++ code. And we'll see an example of that in just a second. For now, we have, let me close all of these files. We have a C++ file called define.cpp. And what we can do with Clang or G++ is use the -e flag. So I'll say Clang++, standard equals C++23, -e, then my source file. And what that will do is it will produce the preprocessor output. And I actually want to redirect that into something like translation unit.cpp. Okay. So I just produced the preprocessor output for define.cpp and put it into translation unit.cpp. And we can look into translation unit.cpp. And what we'll see is that it is a very, very, very large file. If we scroll all the way down to the bottom, it has about 64,000 lines. And the reason for that, once again, is that we included IOStream. And IOStream is a standard library header. It probably includes a whole bunch of other files, which in themselves include a whole bunch of other files. So that's why this translation unit is so big. But down here at the very bottom, you can see the 4 lines that I wrote, right? We have int main and then cout our macro. It actually replaced that macro for us with 350, right? Because that's how we define x to be 350, and then we printed x. And the preprocessor replaced that as expected. So that's the -e flag. You can use it to inspect your translation units directly. The result preprocessor output, like we said, it can be compiled and run just like any other C++ program. So if we say Clang++ standard equals C++23 translation unit.cpp, and then we just run the resulting executable, we're going to get the same exact thing as if we had just compiled and ran define.cpp. Because it's just the preprocessor that's running. So that's kind of cool. Your translation unit is still valid C++ code. All right. In these notes here, I have like this table of preprocessor directives and their brief definition, if you're interested in that. Otherwise, we will move on to part 2 of the build process, which is the compilation step. During the compilation phase, the compiler takes the preprocessed output and converts it into an object file. Now, this section is going to offer a brief overview of the compilation process. That's how we're going to start. But this is like by no means the best resource for learning about compilers. I'm not a compiler designer. And my only goal is really to give a high-level understanding of what's going on to help support your knowledge of C++. So, yeah, that's what we're going to do. The compiler compilation process is broken into 6 major stages. First, there's lexical analysis, which is where the compiler breaks up your code into tokens. Tokens can be like keywords, identifiers, operators, etc. For example, this line might get tokenized like this, where just every single symbol is broken up. And at this stage, the compiler could detect errors, token errors, like just some random symbol sitting around like this. Int at main doesn't make any sense. The compiler could determine that here. Next, it's going to do parsing, where it looks at the set of tokens that it's given and determines if it follows the syntax rules for the language. So we have like int x is 42. Of course, this is valid C++, but this is not valid C++, even though they use all of the same symbols. And that's what the compiler will detect at this stage, is that the tokens follow the syntactic structure of C++. Next, we have semantic analysis, where the compiler will check the code for like logical correctness by analyzing the output of the syntax analysis step. This step will prevent you from doing things like assigning a string to an integer here, which even though it's like valid syntax technically, it doesn't make any sense and it's semantically invalid. So the compiler will catch that here. Next, we have intermediate code generation, where the compiler has now confirmed the correctness of your code, and so it translates it into what's called an intermediate representation, which is like a low-level representation of your code that's independent of the target machine. And why does it do this? It does this to make the code easier to optimize and port to different machines. Code optimization now. This is a step I want to talk about a bit more, because there's a point I want to make at the end of it. The compiler attempts to make your final executable smaller, faster, or somehow or other more efficient without altering its intended functionality. And modern compilers are quite sophisticated in the optimizations they're able to perform. Some basic optimization strategies. We have constant folding, where the compiler can replace an expression like this with just its evaluation. And this avoids the need for a runtime calculation. It can do loop hoisting, which is where you're removing repeated computations from a loop body. For example, if we have this calculation going on inside the loop body, the compiler is able to pull it out because it doesn't depend on the iteration of the loop. Then there's dead code elimination, where if the compiler realizes that some code can never ever possibly execute, like this line here, for example, it can remove it. And because why would it bother writing that to the executable if it can never be executed? And then finally, we have common expression removal, which is where you're just removing redundant computations. For example, if we define A to be x times y and B to be x times y times z, well, we don't really need to calculate x times y twice if we just reuse A. So that's something that the compiler can do. Now, here's the point I want to make. Those are just some basic optimization strategies. There's like many more, and some of them are much more complicated and cool than these ones that I've demonstrated, but this is just to give you like a sort of basic idea of what the compiler can do. In general, you should avoid sacrificing your code's readability for micro performance improvements. And the reason is basically that the compiler is just going to optimize better than you, and it's going to do it in a nicer way. So an example of what I'm talking about, I've seen code that looks like this. I've seen like this exact code, where the person's writing a function to calculate the log base 10 of some integer, and okay, they do it with like a normal algorithm. We just set log to be -1, then we say, well, I is 1, I is less than or equal to n, we increment our logarithm, and then we multiply I by 10, except this programmer didn't want to multiply I by 10 because they thought multiplication was too slow. So they did this. I equals basically I times 8 plus I times 2 done with bit shifts, which is, technically equivalent to I times 10, but it hurts my eyes to look at as the reader, right? This is much harder to understand than I times 10. And so that's why I take issue with it, first of all. It's harder for me to read. And one thing that you should know if you're going to be a programmer is that your code should be meant to be read, not written. You're going to be reading code like 10 times as much as you're writing code. So, okay, that's the first issue with it. Now, the second issue is that there's no actual guarantee that this is going to be any faster than this. Just depends on the chip, really. Like some chips have fast multiplication, and it's going to be faster than 2-bit shifts plus an addition. And I don't know if it will be faster on any given chip, but I think that there's a chance that it could be. But then, the real problem is that if it was faster, then the compiler would just do it for you. And I can prove that it would do it for you. So that's what I'm going to show here. We'll say Clang++, standard equals C++ 23. We're going to compile log10.cpp, and I'm actually going to compile it with the -s flag, which will produce an assembly file. And then I'm going to use -o. We're going to see some of these flags in just a minute, but I'm trying to make a point right now that the compiler can do optimization for you. I'm going to do -o3 -o log10.1.s. Okay, so what are we doing? Compiling log10.cpp into an assembly code with maximum optimization into a log10.1.s file. And then I'm going to alter log10.cpp, and we're going to change it to use the multiplication now. So before we were using the bit shift addition, now we'll use the multiplication. And I will do the same thing, recompile, except I'm going to put it into log10.2.s. And then what we'll do is we'll just see the difference between log10.1 and log10.2. There's no difference between log10.1.s and log10.2.s. Even though we did a multiplication in one and a bit shift in the addition in the other, the compiler just decided which one was faster and optimized the slower one into the faster one because it realized that I could do that. So that's the point that I'm making here, is that any compiler will perform this optimization for you without hurting everybody's eyes in the process. Note that what I'm not suggesting that you shouldn't optimize your code, just that you shouldn't make like micro optimizations that hurt readability, because the compiler is going to do that for you in all likelihood, and it's going to do it better than you too. On the other hand, like algorithmic optimizations are pretty much worth your attention all the time because the compiler generally can't identify those on its own. Okay, now the sixth step of the compilation process, which is the final phase. The compiler translates the optimized intermediate representation into machine code that's specific to the target processor. This is what the CPU can directly execute. Okay, and now we'll move on to the compiler output, which, like I said before, is an object file. Object files typically have a .o or a .obj extension, and what an object file contains is machine code that the processor can understand, but it's not yet a complete executable program. To produce an object file with G++ or Clang, we use the -c flag, which says to the compiler, compile the file, but don't perform the linking step. So as an example, let's say we have a C++ file called main.cpp, and this has like, a variable x, a function multiply, and the main function. And what we can do is say clang++ -c main.cpp, and that will produce a file called main.o, which we can look into now. But we're not going to learn much of anything because these object files aren't typically very human readable. It's just a bunch of gobbledygook to me. So we actually need to use a tool to understand what is inside of this object file. And the tool that we can use to do that is called objdump, object file dump. So we use objdump -t. What -t says is to display the symbol table for the object file. And the symbol table is sort of like just a table of symbols, if you can believe it, where symbols are like variables or functions or otherwise, and it just contains information about those symbols and their memory addresses and whatnot. Okay, so we'll say -tc. C will make the output human readable, so it's like not totally mangled up names, and then we'll call that on main.o. All right, and here's the symbol table. And inside of here, we can see some names that sort of resemble our main function, right? So it's cat main.cpp, our main file. We have an integer x, and here we have a piece of data called x. We have a function multiply that takes two integers. Here we have a function multiply that takes two integers. And here's our main function. So that's kind of neat. You can use the objdump command on your object files to see like sort of what actually exists inside of there. Right, so understanding the symbol table can give you insight into how the compiler translates C++ code into machine instructions, especially when it comes to template programming. If you want to see which templates are actually being instantiated, this is a good way to do that. You could create the object file and use objdump to look at the symbol table. All right, another way that you could examine the compiler output is the -s flag, which we saw earlier. It converts the C++ code into assembly, so we'll say clang++ -s standard equals C++23 main.cpp. That will produce main.s, which is of course an assembly file. And you could go through, examine this assembly file, and gain some insight into how the compiler translates your C++ code into low-level instructions. Now we're onto the compiler flags section. This section provides a directory of commonly used C++ compiler flags for Clang and G++. To view the list of available flags for your compiler, you can use the relevant help command, which will display a much more comprehensive list than I have here. What I have here is just the most common sort of helpful flags. Worth noting is the -o flag, -o, which you can use to specify the output file. We saw the -e, -s, and -c flags. There's various warning flags, which you can use to enable or disable certain compiler warnings. There's some optimization flags, like you could enable different levels of optimization or perhaps optimize for a reduced binary size or etc. And then there's some additional flags. We've been using the standard flag to control which standard we're using. There's the -v flag, which displays some verbose compilation details, as well as this list of other flags here. Feel free to take a look at these notes. They should be in the video description if you're interested. All right, so on to the final stage of the build process, which is the linker. The linker is a program that's responsible for combining multiple object files into a single executable program. It resolves something called external references, which are references that sort of reach across translation units. To illustrate how the linker works, I want to basically look at a case study, which is a project comprising 3 files. The first one's going to be just project.cpp, which is sort of like the main file, I guess you could say. It has the main function. And it includes a header file called foo.h, so let's look at that. Foo.h just declares a function called foo, if you can believe it. And then the definition of foo, recall, would go into foo.cpp typically, so that's where you'll find that. It's just going to print out this message here. Kind of useless, but nonetheless, that's what this project does. Okay, so we want to build this project, right? This is a video about the build process. How do we build this project? Well, let's try Clang++, standard equals C++23, proj.cpp. What you might expect to happen is that because we included foo.h within proj.cpp, everything will work fine. But we actually get an undefined symbol error, foo. The compiler says that foo is undefined. And you'll notice here that there's this LD that actually means it's a linker error. So that's good to be able to recognize instantly, is if you have a compiler error or a linker error, and the LD indicates a linker error. So it states that the symbol foo is undefined, and this happens because foo is defined in a different translation unit. It's defined in foo.cpp, but the linker is unable to find that because it only knows about proj.cpp. And how do I know that it's the linker's fault? The linker can't find it. Well, of course, if I do this and I just compile project.cpp, then everything will work fine. It will produce project.o, which we can actually obj dump like such and look at the symbol table. You'll notice that foo is in the symbol table, but it's undefined where it actually is. So that's what it is. It's an undefined symbol. We don't know where this function foo is. So why don't we do this then? We'll clang++ std equals C++23-c foo.cpp. We're going to compile a different translation unit now, and we'll obj dump -tc foo's thing, and you'll see that there's a bunch of garbage in there. And why is there a bunch of garbage? If you ever see a bunch of garbage, it's probably something to do with the standard library, and that's what it is in this case. But I can run objjump.tc, and then I'll grep it into foo, and that will give us our function here, foo. Okay, so now what we need to do is combine these object files. We could do clang++ proj.o as well as foo.o, and that will produce a final executable, which I can run like this. That last step here, this command ran the linker. The linker combined the object files into an executable. Yeah, so basically, whenever the compiler comes through here, comes through project.cpp, it sees this function for which it doesn't have a reference. It doesn't know where that function is in memory, so it doesn't know how to call it. But it basically says like, okay, programmer, I trust you that this function actually exists. And I'm just going to hold off on where it actually is in memory right now. I'll let the linker take care of that. And that's what it does. That's why it produces the symbol table just fine, because it allows the linker to find the actual function definition. And that's what the linker's job is. So that's why we're able to pass the object files into Clang like this and produce an executable. There's, of course, a faster way to do it. We could just say Clang++ -std equals C++23 and then pass in both translation units, both .cpp files from the get-go. And that will produce the executable immediately so that we don't have to go through the tedium of writing all of those commands. Okay, wow, that was a bit of a marathon, but we got through it. That was the C++ build process. I hope you found this video useful. If you have any questions about anything that I talked about today, or how it relates to C++, or how you could explore further, please feel free to let me know in the comments. Otherwise, thank you for sticking around, and take care.